So can you hear me at the back today? Sorta? Okay. All right, welcome back. As you might recall, I'm picking up this story a little bit in the middle of something, so it's a bit of a context switch. So maybe first I should remind you, this is the last thing I had up. Let me remind you of the story so far, right? I just introduced this sort of core problem that I was using more or less to organize a guided tour of, sort of some big section of machine learning research. The core model we were looking at is learning a linear function from data, which, although simple looking, is quite powerful for many reasons. And the first part of the presentation was meant to convince you of this by first showing how we could generalize the input side of a linear function to incorporate nonlinearities of various forms, and this would help us, more flexibly model data. Of course, with flexibility comes a price, and the price that we saw, at least intuitively, is this risk of overfitting the data. And so we introduced, as sort of countermeasures to this, two different regularization strategies. I briefly mentioned feature selection or model selection, but focused on two regularization strategies. One, Euclidean regularization, both of which are simply trying to bound the weights of the linear function or the slope. Euclidean regularization, you'll recall, led to the representer theorem, which as a consequence led to Hilbert spaces or reproducing kernel Hilbert spaces, or the kernel trick. Then we stepped back and said, okay, fine, Euclidean regularization, just move on. Let's look at sparse regularization, in particular L1 regularization, which has a non-differentiable point at 0. And this has the feature of performing a sort of implicit feature selection, where many of the weights in the solution are locked in at exactly 0, and hence the corresponding features are removed from the model. Then, and you might remember this, then we got to the point where we sort of saw these two different approaches, and they had fairly dramatically different properties. One a feature selection property, the other one mapping things implicitly into some high dimensional, or in fact even infinite dimensional feature space. And it sort of raises the obvious question of how compatible are these two things? Could we put them together? And we discover, first off, that the answer is no. At least if we think of combining these two ideas in a very naive way, we're not going to get far, because if we simply add this term here to our optimization objective, a little bit of sparse regularization, it immediately blocks the representer theorem. And if we don't have the representer theorem, it means we can't have an equivalent adjoint formulation to the formulation we started with, which means we cannot exactly represent the original learning problem in an implicit feature space. That's kind of a drag. So as you might imagine, people have thought about this and tried to tackle the question of combining these two things. So where I want to pick up this story is just to complete this discussion of what it looks like to combine these things, at least the way people are conceiving of it now. And we'll see what's both interesting and compelling about this, but also what's a little bit problematic and I think still meriting future research. Yeah?
You said you can't combine it, but I mean, you could pose an optimization problem where you do combine.
Absolutely. Absolutely. The one thing you learn about researchers, especially if you try to publish, is they're dogmatic, right? And so they'll say, no representer theorem, next. But you're right, in practice, I mean, sure, it's a coherent problem, it's tractable, it's convex, go for it, right? Yeah. Oh, yeah. Yeah.
Does that mean that if you do optimize over this, just naively say, oh, you're now solving a different problem, it's not guaranteed to be the same problem, that you kind of change the objective? Is that kind of the...
Yeah. Boy, you guys are hitting me with the hard ones right away. It would sort of be, I guess, what does it mean to combine these two things, right? And what kind of feature space are we working in? I'm gonna, hopefully a better answer comes to me. The only thing that we're going to lose for sure is an exact representation in an adjoint form. We know we lose that for sure. Whether you should care about that, actually, I think that's a legitimate thing you should be thinking about. There was just one more question.
I wanted to ask about features. Features mean so many different things. Are you referring to the parameters of when you say feature selection, what exactly?
Yeah. Yesterday morning, I actually sort of went through about maybe almost an hour, but I went through a sort of a guided tour of like many different thoughts about feature construction. You know, things like polynomial expansions or different basis sets, trigonometric expansions, local basis function expansions, and so on. Those are generic. Of course, in any particular application, sort of the key concept is, you know, application engineering really is largely focused on, you know, designing features that are important for the map you're trying to learn in that application area. So yeah, I'm just assuming as background, we've got some big set of features in mind, in fact, too big. And we're fighting this battle of trying to keep it down. Okay, so let me complete this story. All right, so here we are. Foolishly, we're up against dogmatic reviewers, and we want to get the representer theorem. Okay, and we're not going to get it this way. Okay. By the way, this is also a cheap excuse to introduce you to some other interesting optimization concept along the way. So it's worth doing anyway. So here's one way, anyway, about one way to continue to move forward here. And the idea is it's a cheat, so it's a bit of a hack, okay? The cheat is what we're going to do is we're going to decouple this weight vector here, and we're going to introduce a new sort of parallel weight vector, mu, which is a weight vector also over the features, so it's going to be parallel to w. But what we're going to do is try to, you know, ideally mu would be a feature selection variable, and it would be a discrete Boolean variable, 0, 1 variable, and it would knock out features or keep features. But of course, we're going to lose tractability, probably, if we just naively look at a Boolean constrained optimization. So we'll just relax this mu variable to be a vector variable, say, between 0 and 1, some relaxation of Boolean selection variables, okay? All right, so if we combine, you know, kernels with feature selection, we would basically see this process of kernel selection. Okay. So what is kernel selection going to look like? So first, just some very, you know, trivial linear algebra, but it helps us actually see both the simplicity and the power of what we can do here. So we want to stay inside the representer theorem, which means we're really going to be interested in this kernel matrix, which is the outer product matrix of the features. Now, just to remind you, one of these feature matrices phi is like size of training data by number of features, okay? And then the phi transpose is a square matrix. It's size of training data by size of training data. Every entry is an inner product between two feature vectors, okay? However, that's not going to be a very convenient way to think of this. So equivalently, let us just sort of refactor this matrix in a different way. So I could rewrite this product as actually a sum of these outer products. So what is this here? Oh yeah, and I can explain my Matlab notation. So if I have a matrix and then I have a subscript with a colon and a j, you know, that's Matlab notation. So I'm going to, you know, take the colon to be the whole column, and this would be like the jth column. Okay, so I can rewrite this outer product matrix here as a sum over these rank 1 outer products. The outer product of the jth column, right, sum j equals 1 to all the features. Okay, and this is, you know, you've seen this before in first year linear algebra or something. This is just a rewrite of that matrix. So this is going to be rank 1. It's an outer product between a column vector and a column vector transpose, so it's a rank 1 matrix. And so we'll give a name for that rank 1 matrix, call that kernel matrix K sub j. K sub j is a kernel matrix. It's a semi-definite matrix. It just is kind of a silly one because it's a rank 1 matrix, but it's still a valid kernel matrix, okay? And in fact, we don't really care that that kernel matrix Kj is rank 1. Let's just say it's some kernel matrix, okay? So instead of thinking of a set of features, what we're going to do is think about having a set of kernels, but this is equivalent to thinking of it as a set of features, right, in the adjoint representation. Okay, so we have our set of kernels, from among which, right, we want to, you know, do some kernel selection, or equivalently feature selection, okay? All right, and so here's how we're going to go about it. We're going to introduce a weight for each feature. So just one more little bit of tedium here to set this up. So I'm going to consider a new feature matrix. Okay, so we start with our old feature matrix here. And then, sorry, I have to explain my notation here one more time. So I have this big delta of mu. That's just notation for diag. Okay, so when I have a big delta of a vector, all that means is just taking that vector and putting on the main diagonal of a matrix. Again, this is just linear algebra playing around here. And I'm taking a square root for reasons that you'll see down here. But what I'm doing here is I'm just taking that feature selection vector, and post-multiplying the feature matrix. And all that's going to do is for each feature, I'm going to multiply the whole feature, right, by its corresponding weight. So if mu is 0, 1, you know, that 1/2 doesn't matter, and it's just feature selection, and it's going to zero out columns. Okay? So this is how we could represent mu as a feature selection variable. Okay? But in the adjoint form, what's going to happen is that we're going to get some new adjusted kernel, k tilde, which is going to be the corresponding kernel to the adjusted, you know, selected feature representation. Okay? And if we stick it in that outer product, what we find is that we have the original feature representation with this diagonal feature selection variable in the middle, selecting features. Okay? And then again, the same sort of rewrite, we can rewrite this thing as a weighted sum of the individual kernels. This is really an exciting way to start the day. But anyway, so we see the representation. Okay? So we have a linear combination of kernels where the combination weights are given to us by the feature selection variables. So this is what we want to do. We want to set up the problem the way we had it before, but now we have the auxiliary variables. The problem before was to minimize loss with respect to W, or the adjoint variable A. All we're going to do is try to minimize the loss with respect to both that variable and this feature selection variable mu, where we impose some, say, sparse regularizer on mu, trying to zero out columns. Okay? Just as an aside, though, that isn't going to work, and we're going to need to do some engineering to do it. And I apologize, bad slide design. Actually, don't look. Let me skip ahead and show you what I'm talking about. If we just sort of naively forge ahead with what I've shown you so far, this is what we would get. Okay, so we've got our feature selection variable. We have our original feature variables. We have our loss function, and our loss function is now being expressed with respect to the adjusted feature representation. And we have our nice Euclidean, you know, regularizer on the weights, which is giving us representative theorem in kernels. And then out here, for example, we could put a sparse regularizer in feature selection variables. Okay? And so this would be our computational problem. We just want to jointly minimize with respect to both the original weights and the feature selection weights this objective, which is our regularized loss. Okay? Seems fine. The problem is, if you look at this problem as a function of these two variables, mu and w, this is not a nice function at all, right? We have this square root in here. We have this interaction between mu and w there. This looks like a horrific optimization problem, and it likely is a horrific optimization problem. Okay, so to actually pull this off, you need to play optimization trickery and reformulate this problem as this problem. Okay, so just as an aside, I think it's worth showing you, yet another instance of a nice way to reformulate an optimization problem, because this trick here is very useful. It's not just useful here; it's useful in many other circumstances. So at least I'll give you some introduction to how we go from here to here, and then I'll try to come back and explain to you why this is actually tractable. Okay. Okay. Close your eyes for a sec. Okay, so we were here. Here's the aside. So it turns out that what we're going to have to do is that inner minimization problem over W is a convex minimization on W, but it's interacting with some other variable. It's going to wind up that we need to dualize that problem. As you would know, right, an optimization problem is never sort of cast in stone. If I have some optimization problem, I always have available to me a whole suite of equivalence-preserving transformations of that problem. So I can rewrite some particular optimization problem as another one, say a primal and a dual, for example, where I preserve equality, right? So the value of the optimal objective doesn't change and so on, okay? So we're going to deploy one of these strategies here as sort of a trick to get around the apparent intractability of the joint training over the weights and the feature selection vector. Okay, so just an aside. So what we're going to use in this instance is Fonchel duality or Legendre-Fonchel duality, just jargon. And I'm just going to sort of give you a quick preview, and I think other speakers will go through this in excruciating but really useful detail. Okay, but the preview is pretty easy. Let's just simplify notation and say we start out with some convex function of a variable we care about, right? So L of W, say convex in W. Okay. Well, we're going to try to reformulate a problem instead of as a convex minimization, as a concave maximization, right? So we're going to get this kind of primal dual matching problem, okay? And here's the key concept we're going to use is the idea of a conjugate function of this function. So this is just a definition. So if you give me any function L of W, let's just define the Funchal conjugate just to be this thing here, okay? And what this thing here is that it takes your old function, negates it, and then does a supremum, a maximization over your variable of some linear term here, parameterized externally, minus that function. So let's say you had a convex function, it turns it upside down, it's concave, and then we add a hyperplane, right? The hyperplane is fixed externally, and then we're just finding the maximum value over your original parameter space. I'm sorry, I should have drawn a nice picture for you, but anyway, it's just a definition, okay? It's a very easy definition, and it has some very nice properties which are immediate. One definition is this function, L star of alpha. So alpha is some new parameter. Alpha, though, has to be a parameter the same size as the original parameter. Okay? So we'll call alpha a dual parameter, probably. But it's a dual parameter the same size as the primal parameter in this case. L star of alpha is the function we've defined by its construction is guaranteed to be a convex function. In fact, L star of alpha is guaranteed to be convex no matter what L of W was. And why is that true? Because alpha only participates in this in a very simple way. It only participates linearly inside, and then we have a max of linear, right? So you draw a bunch of lines, and then you take the upper envelope, and you always get a convex function, right? So just by construction, this is convex, okay? If the function L itself happens to satisfy some stronger properties, like L is convex plus a technical condition that it's closed, then we get a wonderful tight equivalence representation. So I'll explain closed momentarily. So if L is a closed convex function, then we get this strong duality property here that if I take one conjugation and I get the dual of the first problem, and then I conjugate again, I get back to the original problem, okay? The technical condition here of being closed is somewhat benign, although it'll kill you if you ignore it sometimes. All it means is if you look at a function, right, think of its epigraph. The epigraph is just the set defined by the points above the function, right? So if you just look at the set of points above the function, is that a closed set? And if that's a closed set, then we get this strong duality property here, okay? So as a consequence of this, we now get this. What we can do is we can re-express the original objective as actually as a sort of a variational form, as an optimization of some auxiliary variable, alpha, where we just maximize, in fact, over alpha, some linear function minus this convex conjugate function here, okay? Now, whether this helps you or just causes you useless headaches, usually boils down to whether or not you have a nice form for that conjugate, L star of alpha. And so if you pick some harebrained function and then you try to compute its dual, you probably will never get a closed form. And if you don't get a closed form, this is not likely going to help you, okay? But in our case, we have very simple loss functions, like say squared loss or absolute loss or something similar to that. In those cases, the corresponding conjugates are, well, you can just look them up. They're well known, okay? So we can have an efficient way of computing the dual function, and so this will be maybe a useful thing. Okay. So here's how we apply this, right, to our setting. So we're not worried about feature selection yet. What we're worried about here is just reformulating the convex minimization over the original variables as an equivalent concave maximization over the auxiliary variables, okay? And just by direct application, if we apply the duality that we had before, the convex minimization here can just be written as an equals, like literally the same objective value, of a concave maximization. And so we can see the alpha here winds up being in a minus convex and also a minus convex quadratic, right? So this is a concave maximization problem here. There are no local maxima. There are only global maxima. And given the strong duality property we had before, there's no duality gap. That is, this by weak duality would always be a lower bound on this, but in fact, when you do the maximization, there's no gap and they will be equal, okay? And the conjugate here, what we're doing is we're taking the conjugate of the loss function on the first argument, right? So the first argument is the argument that we're our linear model parameters are participating in. Okay. Great. So for this problem, we can equivalently rewrite it this way. And actually, just by accident, notice something interesting is that it's automatically expressed in terms of the kernel. So we knew representative theorem would hold. We knew we should be able to rewrite this as a problem that's expressed only in terms of inner products. And actually, in this case, it's happened for us already. So we don't even need to do further reformulation. Okay, so this would be a typical like dual form of training for sort of a standard loss minimization framework with Euclidean regularization. Okay. And then putting the pieces together, this is what I showed you before. So we start out with this joint minimization where we've now introduced these new feature selection variables, and we've introduced some penalty on those feature selection variables. We've relaxed them to be not Boolean selectors, but at least between 0 and 1 selectors. And we put in this horrific mess, but if we take the inner problem here in W, we can, as we've already seen on the previous slide, we can write it exactly as a concave maximization in this auxiliary representation alpha, okay? And so that's all I'm going to do. I'm just replacing the inner minimization with this inner maximization. And then I'm just going to look at this form that we get, and I'm going to declare victory. Okay? So let me just explain to you why we can declare victory at this point. Well, this we know is tractable already. This would be concave maximization problem, well, provided that we have an efficient representation for L star. Concave maximization problem with no local maxima. In fact, it's smooth, and we could just, well, it's likely to be smooth, and we could just apply standard mathematical programming techniques there. The interesting thing is, like, why is this now an easy problem with respect to mu? Okay? Well, what we actually have here is a problem that, with respect to these two variables, it's like a game, right? We have a minimization player and a maximization player. And if we look at the game matrix, or the objective that they're playing for, we'll see that it's a concave convex problem, right? So this inner objective, the inside part, is just linear in mu, okay? So if I'm the mu player, and say I go second, or first, sorry, I'm the mu player out here, the other player gets to maximize. But from my perspective, the other player, all he's doing is he's maximizing linear functions. Okay? So from my perspective, this whole inner mess is just some function of mu that is a convex function of mu. Okay? So the mu player's happy. This mu player, it's just minimizing some function. It's a convex function. There's no local minima, only global minima. Now, computationally, you may not want to tackle it directly this way. You may want to reformulate. But in terms of understanding whether there exists a tractable solution, you could already solve it this way. Okay? The way you would solve it, though, is with a nested loop, right? I have some outer minimization on mu, and the outer minimization on mu just calls some function, right? That function just has to solve some hidden auxiliary maximization in some variable we don't care about, and it gives me numbers, and I could even get subgradients, and I could descend. Okay? It's just that every function evaluation is a bit expensive, right? Because every function evaluation has got to go off and solve some auxiliary maximization problem. Okay? Anyway, to continue, we all know that from the perspective of the max player, that this is also an easy game because he has a concave maximization. Okay? So we went from looking at a joint training problem that was really quite messy to a joint training problem, okay, that looks really messy, but has a nice property, which is there are no local solutions, right? If you solve this problem, you find an equilibrium between these two players, which you can do by just running the outer search to minimize this inner maximization. Then you've got victory. You've now solved for the optimum feature selection variable. Okay? Once you've acquired the optimum feature selection variable, well, you could, I sort of suppressed the relationship between alpha and W, but you could directly recover alpha and then use alpha to recover W. Or worst case, you could take the mu that you got here, plug it in here, treat it as a constant, and recover the W directly. Either way, you could solve this problem now. Okay? Whew. All right, so when you pick up your random JMLR or NIPS paper, and that's what you see, right? You see this kind of depiction of a problem and all this manipulation to try to get to something that looks reasonably tractable, then a few happy graphs at the end, all right? I don't want to sort of just stop this way. So let me just sort of suggest what else you might see here. Definitely you would see reformulations of this computational problem into other convex problems that are even sort of more efficiently solvable, okay? The real thing that we've lost with all this optimization reformulating is this a good idea, okay? Does it actually work? And here's kind of the embarrassing, not so secret thing about kernel learning is that the results that people are usually able to pull out of this kind of auxiliary variable feature selection nonsense is not great, okay? This is not proved to be sort of like a sledgehammer that you can just throw at every problem and boost your performance. Not even as robustly as simple regularization would be without feature selection. So if you look in the literature right now, actually there's quite a proliferation of papers. What are these papers doing? Well, other than optimization reformulations, what they're actually doing is they're starting to explore what's going on with this feature selection variable. Should we really just do L1 regularization? Should we do L2 regularization? Should we do LP regularization? Should we do some other fancy kernel alignment type regularization? Okay. Maybe those are good ideas. The one thing, though, that we shouldn't lose sight of is that maybe this wasn't a great idea to begin with because we've got this interaction, right? So, in this effort to sort of wiggle around the feature selection versus representer theorem issue, we've now actually introduced this auxiliary variable right into the model. And so it's interfering with the linear model W that we're learning. Right? And we could try to pull it out later, but now W was trained in the context where there's some mu. So if you pull that mu out later, it shifts your hyperplane, and that's probably not good. Okay? So you probably keep the mu as part of the model in future test cases, but now mu was trained in a fairly weak indirect way here, right? So I think actually that a lot of the research, even though right now it's focused on changing the way we would regularize mu, likely there's a need for some pretty reasonable research to understand, is this really a sensible thing to be doing even from the onset, right? Because the results, let's face it, haven't been super stellar. So this may actually just be a hack. Okay. But anyway, interesting hack, and it was an excuse to show some duality. Okay, so, okay, not fun. So this is the type of lecture I was hoping to come at the end of a session, not at the start. But let me now just move on to the next sort of small topic. Oh, unless there are questions about this. Yes?
So I am wondering, because both L1 and L2 are trying to deal with the overfitting.
Yeah.
Okay, they are really overfitting for the L2 norm because it introduces like infinite feature space. What does that mean? Does that mean to tend to overfit the infinite? Because when we have more and more features, we can
It's guaranteed to overfit. So really, whiteboards are better than slides, I got to say, because I could draw a picture, okay? It's guaranteed to overfit if you don't regularize. Why? Because if you don't, so say you're in a kernel space with some infinite dimensional feature representation, but you sort of relax the regularizer, right? So we always have to have some L2 regularization, but you'll make the regularization weaker and weaker and weaker and weaker, okay? Well, what happens? This isn't going to show it. What's happening is you're going to start to get to interpolation, right? The kernel matrix is likely to be full rank. So I'm now training the dual weights, which are going to be on the kernel matrix, right? And so as I relax the regularization, when I have like a full rank kernel matrix and a target vector and then some weights, I'm going to be able to just solve that linear system and get zero loss, right? The only thing that's keeping me from exactly overfitting the data, like literally interpolating, is the regularizer. So what you said is correct. If we're doing kernels, we're in some high-dimensional implicit feature space. You absolutely are at grave risk of overfitting, because in fact, you could exactly fit with that kernel matrix and dual weights on that data.
But isn't that paradoxical, because the purpose of L2 norm is to avoid overfitting, but when you have the L2 norm, it introduce the kernel and you tend to overfit. I just can't understand.
You call it a paradox, I call it a dilemma. So there's always this trade-off, right? So we always want more flexibility, which means we always want to overfit. But then we always don't want to overfit, we want to avoid. So look at it this way. We want to avoid underfitting and we want to avoid overfitting, right? It's just that we have sort of two different mechanisms in play to deal with both of these issues. So to combat underfitting, we enrich our representation. We add kernels, we add features, right, to allow the model more flexibility. But then to combat overfitting, we regularize, we try to select features. I didn't do anything. Okay. That's the machine learning question, I would say. Okay. All right. Sorry. Any other question? I wanted to move on, but that's okay. Before you ask, the next topic is cooler. Okay. So, okay.
So when you use the L2 regularization,
yeah.
you go for catches.
Yes.
Okay. So if you try to combine,
I'll repeat the question. Yeah.
So when you go for combining both of them in the naive way, do you go for these spaces that are called crane spaces, or that's not really related?
I go for them.
Crane spaces.
Crane spaces.
Yeah. Reproducing kernel crane spaces where you have negative definite kernels.
Yeah, negative definite kernels. I haven't actually looked into that much, but I know people do. I have no answer to that question. So the question is, why not look at reproducing crane spaces?
I'm wondering if it goes there.
Could go there. Has it gone there already is the real question. Probably. Don't know. Okay. Okay, good. Next topic. So this is the last thing I want to cover in the first sort of major topic. I'm still on lecture 1. The first major topic I wanted to cover was how we can take simple linear modeling and make it more flexible, but also combat overfitting. Okay? There's one more major sort of predominant strategy out there for dealing with large feature spaces that is different from what I've shown you so far, based on this idea of boosting. So I just want to give you a brief sort of general view of a completely different approach to the problem of training on large feature spaces, which sometimes is very empowering and can get you out of a tough spot. Okay? So this will be the last thing I cover in terms of regularization and input representations. So boosting has an interesting and long history, and there's many perspectives and ways you can look at it. As you might guess, I'm going to ignore all the other perspectives and just give you the simple one, okay? That it, in fact, isn't about history. It's just about the idea. So the most sort of widely useful way of thinking of boosting is really in the following sense. We want to be able to train on large feature sets, okay? Let's say, in fact, we're back to the setting where we have an infinite set of features. Okay, but we don't have a kernel. So what if I give you some feature representation, I just make it up, right? I stick in a bunch of polynomials and a bunch of parameterized, trigonometrics, parameterized local basis functions, whatever. I just throw a bunch of things in, okay? And maybe the features themselves are parameterized so that there's not actually a finite set of features. There's an infinite set of features. All the features I could express by some parameter. Okay, well, great, I have an infinite set of features, and I can say, how can I train with infinite feature representations? And then we say, we have a trick. It's called the kernel trick, right? So all I got to do is devise a kernel that implicitly computes the full inner product over this infinite feature set that I made up, okay? And the problem is, in general, if you just make it up, you didn't make it up to allow you to compute a kernel on it, you just made it up. And what you usually encounter is a setting where you have some interesting feature representation you'd like to use, but you have no kernel for it. what are you going to do? Okay, you could give up, you could do something else, right? But no, what you can do is a boosting trick. Okay, so this is a scenario we should be thinking of. We have some infinite feature representation, every feature, say, perhaps parameterized somehow. And we'd like to learn still a linear model on top of that infinite feature set. Now, if I'm learning a linear model on top of an infinite feature set, let's just think carefully. There's a couple of ways I could represent that linear model. The way I'm going to think of representing that linear model is in a sparse way. I'm going to assume that the actual thing I represent on my computer is expressed by a finite choice of bases out of that set. So I can only ever represent a finite length feature vector, a weight vector. So I'm just going to assume that I have a sparse linear model, some finite set of weights over the infinite bases. Okay, you could try to say, well, express non-sparse models, which we think of this way, like a full integral over the whole set of basis functions. You could go that way. The problem if you do that, though, is you're going to be heavily constrained by integration problems that you can actually solve and express. Because remember, it's not just training. You're going to learn the linear model, and now you get a new test case, and you're going to have to make a prediction. And if that prediction now requires you to do this full-out integration, maybe that's problematic. Actually, that's Bayes, but I'll come back to Bayes later. Okay? Let's for now say, let's agree that it's sufficiently interesting to be able to train over this infinite basis, but still produce a sparse, finitely representable model over a finite set of weights. And then when we get a new test case, it's trivial. We just evaluate the test case on the finite set of features we selected, inner product with the weight vector we learned, predict. Okay? So why not? It's a neat idea. And actually, it's often an effective idea. I have these two kind of historical examples. Maybe I'll just do this quickly. Here's sort of natural ways that infinite bases actually, in the history of machine learning really do come up. So there's sort of two classic ways that we normally encounter infinite bases are decision trees and neural nets. If you haven't learned about decision trees yet, that's good. The next slide is of no value. But if you've learned about decision trees and then you think like, why is machine learning split into these separate communities that don't talk to each other? I want to show you something, which is decision trees are completely subsumed by everything we're doing so far. Okay? So this is just for some, actually, how many of you have ever learned about decision? How many of you have learned about decision trees? Ah, okay. Subsumed. What do I mean? So just quick demo. So what's a decision tree, right? Like you've seen these happy little diagrams. So I take some feature vector, let's say finite, okay? And then I have a decision tree. What it does is it tests one of the features against some value, okay? So I'm going to look at the long feature vector. I'm going to pick like feature I. I'm going to say, is feature I bigger or less than some threshold? If the answer is no, I go this way. If the answer is yes, I go this way. And then if I wind up at some decision node here, I pick some other feature. The feature I pick here could depend on the answer. So this feature is not the same as this feature in general. Anyway, I pick some new feature here, some threshold, and I check, is it yes, is it no, and then I go down the tree. Eventually I go down the tree and I get to a leaf, and then at a leaf I make a prediction. The prediction I'm going to make is just, my guess y, should be y hat, whatever, is some value. Okay? So I have this tree, and it's what the tree is describing in the context that we're looking at here is a piecewise constant function. Right? You get to a leaf, it's a constant, and then the tree is making all these axis parallel splits. So you're taking space, you're chopping it up in these axis parallel ways, and then you're putting piecewise constant functions there. Maybe you like that, maybe you don't, whatever, that's what it's doing, okay? It's just a linear function. What do I mean? I could equivalently re-represent that decision tree just as a linear combination over a choice of bases. What's the basis? Well, the basis actually is coming from paths in the tree. So for every leaf, there's a unique path to the root. If you take that path, what I can do is I can just go along that path and I can conjoin, I can create a Boolean feature, which is 0 if that path is false, you wouldn't have gone down that path, and is 1 if that path is true. Okay? And the interesting thing about these Boolean features, if I create, this is for the first path to this node, second path to this node. If I look at all these features, one feature for each leaf, they're actually going to be disjoint, right? Only one of them will be true on any one example. Okay? So I'm going to say, forget about the decision tree. I have some feature representation. Okay? And in fact, you have to learn the tree. So learning the tree usually involves picking the features and picking the values. I'm going to say, don't think of it that way. Here's another way you could think of it. Just think of all the possible paths. Okay? Say if we have finitely many features, we're going to get, each path is of finite length. And then we're going to look at all, well, let's assume we have finite length paths. Then I'm going to get some basis, right, over those finite length paths. Okay? But the basis will be infinite because each basis function is actually parameterized by these thresholds. So there isn't a finite number of basis functions, it's infinite. Okay? But think of them all, right? So I have this huge infinite basis. What's a decision tree? A decision tree is a constrained choice of a subset of the basis, right? Where it's picked that basis, and in fact all it is doing is an inner product between that basis and the particular leaf values. So you could think of the leaf values as just a weight vector being inner producted with the feature representation, okay? So what's the difference between a decision tree and a linear model? Well, no difference except for some really annoying constraint, right? If you're learning a decision tree, you're learning a linear model over this basis set, but you have this tree constraint, which means if I pick this feature, I can't pick that feature anymore, right? The feature set has to have some coherent tree structured property to it. Okay? The question you have to ask yourself is, how important is that tree structure property to you? You can tell how important it is to me. To me, I'm thinking, nah, if I just forget about that tree structure property, just take the basis, fine basis, lousy constraint, okay? If I throw the constraint away, what do I get? Well, what I gain is everything, right? If I don't impose the tree constraint, I look at the basis, I get all the regularization tricks, all the kernel tricks, everything I've shown you so far, potentially. Right? And everything I'm going to show you, all right? But if I impose this tree constraint, suddenly I'm in this little corner of the world where there's a few people working on heuristic algorithms for solving NP-hard tree fitting problems. I don't know. So, if you have a compelling intuition why you want tree structures, great. But for most people, I think it's a linear problem, okay? Unfortunately, it's a linear problem with an infinite basis set. Okay, so there's not a well-known technology out there for solving them, except there is. It's called boosting. People just don't realize that they could actually train these. Okay, so I'll show you momentarily how to do it. The next classical model that has the same characteristic of an infinite basis is one I've already shown you, is the, say, two-layer neural net, where each hidden node in the neural net is a basis function, but that basis function, say, parameterized by some weight vector between the inputs and that basis, okay? So if I draw a neural net like this, say with like L hidden units, what I'm saying is you have an infinite choice of bases. Every basis function is one of these low-level models, okay? There's infinitely many of them, and what I'm telling you by learning this neural net is that you're going to learn a linear representation, a sparse linear model, but the constraint on that sparse linear model is you get L. You get L basis functions from that infinite set. No more, no less, L. Okay, so you got to go out there, you got to find the L best features from that infinite set, and then on top of those L features, you're learning a linear model. Okay, it's not a fine representation, but the constraint of L is problematic. Okay, so just let it go, and let's just say we don't constrain the neural net to have just L features, but let's let the learning algorithm figure out how many features. Okay, well that's very close to something that's trainable. In fact, we'll see shortly it is trainable, but it's trainable in, in a sparse model way, right? We're going to generate some sparse model and learn a linear combination on a sparse feature. Oh yeah, that's what I was going to say here. And if we want to ensure sort of a sparse representation, we could now regularize, just like we've already been doing, using an L1 regularizer on the top layer weights. Okay, the problem in both those cases is that the basis set is infinite and you don't have a kernel. Actually, for the two-layer neural net, there are some special cases where there's a kernel. People have worked it out. It's amazing, okay? But in general, you pick some representation like this, you're not going to have a kernel. So how are you going to train? Well, here's the idea. So I've already shown you what we're not going to do is enumerate the basis. It's not even countable, okay? What we're going to do is we're going to have a greedy procedure that incrementally grows the basis. So we're going to have a meta-algorithm. It'll look like a meta-algorithm that's basically going to take a current model, and then it's going to try to pick the next feature. And then once it's picked the next feature, it's going to add it to the model, and then it's going to adjust the weights. Okay? And how do we think of a procedure like this? We're going to think of it as greedy coordinate descent. So conceptually, we're just still solving an optimization problem where we have a weight vector, really long weight vector, over a big basis set. And we just have some loss function, which I've now suppressed in here. We have some loss function. Oh, here it is. Okay? And we're just trying to minimize the loss of our sparse linear model with respect to the targets, right? That's all we're trying to do. And it's just a minimization with respect to the sparse weight vector. Okay? But the way we're going to do the minimization, and sorry, one more thing, and we've set up the loss the way we set it up before, it's probably convex, right? So we should be able to solve this problem. In fact, if I have an infinite basis set and a finite set of data, I should be able to interpolate if I really wanted to. I'll come back to fixing that problem, okay? But we should be able to train this, okay? So the way we're going to train it is by thinking of it as a coordinate descent. So what's a coordinate? Each feature is a coordinate. It's got one parameter. If I pick a feature, then I can do a line search in that one coordinate, right, to minimize this function in that coordinate direction. Okay? So, and I'm going to do it greedily. That is, what I'm going to try to do at each stage is I'm going to try to pick the next coordinate, the next direction, in a greedy fashion. Try to pick the coordinate that leads to the steepest decrease in the function. Once I've picked the coordinate direction, I'm going to now do a line search in that direction to minimize the objective just in that direction. Okay? And then update the model, and then pick a new coordinate, new greedy coordinate, update the model, greedy coordinate, update the model. Okay? And the question we should be asking ourselves is this going to work? Is this actually going to converge with a finite model to a minimizer of that objective? And we'll find out actually in very general conditions it will work. In fact, it's not a big surprise. But let me caution you, what we're actually solving here is not a finite dimensional minimization problem, it's an infinite dimensional minimization problem. Okay? Coordinate descent, intuitively, in a finite dimensional setting feels like it should work. It does work, generally, okay? But that doesn't mean it's going to work in an infinite dimensional setting. So let me show you, just think what could go wrong. Well, what could go wrong is if I have infinitely many dimensions and I'm picking a descent direction, I could always pick a descent direction, but maybe the best descent direction diminishes so rapidly that I fail to make progress to the minimum, right? And so in infinite dimensions, you have many ways to fool a local coordinate descent algorithm. And the real question, technically, is how do you know you're not getting fooled? And the way you don't get fooled is imposing assumptions and making strong assumptions about your coordinate selection. OK, anyway, this is the math that says what I just said. I'm not going to go through it in detail. But one final issue. If I want to pick a best coordinate, what am I trying to do? I'm trying to pick a coordinate that leads to the steepest local decrease in the function. If you look at the partial derivative of the function at the current model with respect to, say, a candidate weight, right? That's what we would use to determine how steep the function is in that coordinate direction, right? We would, just take the trivial derivative here. We get to this form. Let me just rewrite this in a more compact form. Evaluating a coordinate, picking a feature, and telling how steep the descent direction is in that coordinate is a simple inner product. All we got to do is we take the linear model at the current solution, and then we get a vector of derivatives under the current model. So every training point, we get a vector, a derivative. Positive derivative, negative derivative. We get some derivative of every training point, okay? And then you have a fixed basis function, say candidate k, and it's going to be a vector over the training data the same length. And you just look at that inner product. So you take the inner product of the feature response to the derivative, okay? And that'll give you a score, and that score is in fact the partial derivative, the local rate of descent, okay? So the coordinate descent procedure introduces what's normally called a weak learning problem, and the weak learning problem is solving that problem. So I give you the outer algorithm hands you a vector L prime, right? And your job now as the coordinate picker, or weak learner as it's historically called, is to reach into your infinite set of basis functions and find the one basis function, phi k, that minimizes this inner product, gives you the steepest descent direction. Okay? So that's a computational problem you have to solve. You pick your infinite basis, decision tree basis, neural net basis. You have to be able to go in there and find the one optimal basis function that minimizes that inner product. Okay? Sounds easy? And then you move on, and so you're writing the paper and you say, let's assume that's solved. And then we run this algorithm incrementally. Okay? I'll come back to that in a minute. And then once we've picked a feature, then we can just do a line search and continue. Okay? Before I get to this question of finding that steepest descent direction, let me show you the theorem, which basically says if if you have a reasonable weak learning algorithm. So it turns out you don't have to pick the optimum descent direction, but you have to pick an approximately optimal descent direction. That seems pretty clear, right? But let's assume that you can devise somehow some algorithm for finding a descent direction, this is the one you pick, that's at least within gamma of the optimum descent. Let's say you can do that. And you can do it always. So for all rounds of the algorithm, you can always guarantee a gamma approximation of the optimum descent. Okay? And if we make some other technical assumptions like bounded bases over the training data, a Lipschitz continuous derivative vector, and so on, so technicalities, okay? Under these conditions, you can in fact show that this works. Your coordinate descent, your approximately optimally greedy coordinate descent procedure is guaranteed to converge to a linear model that minimizes the loss. Of course, if your infinite feature set can span the data, that minimum loss is 0, and it's essentially saying your loss goes to 0, and you're going to be guaranteed to overfit, right? But basically, in general, we know this should work. Okay? So this is the beauty of boosting, and this is what kind of sucks people in, and they start thinking like, yes, I can boost my way out of any problem. Okay? But alas, things are not as easy as they seem, and what's happened is the hardness of the problem has kind of just been swept under the rug, but it's still there. Oh, gee, sorry, one more issue. Of course, to combat overfitting, what we'd like to do is take our original loss and just regularize. Whatever regularizer you like, L1, sparse, L2, non-sparse, pick your favorite, right? It actually doesn't affect much. There's only a slight adjustment in the algorithm, which is the coordinate descent selection is the same. It's just that once you've picked a greedy coordinate, you can't just myopically optimize that one weight. You actually have to jointly optimize the finite set of weights that you've enabled so far. So, and that's true under both L1 and L2. So as long as you go back and do a total corrective update, that is, retrain the entire linear model, then you can still guarantee convergence under these fairly general technical conditions. Okay? Sorry, so that's the only caveat there. So you can avoid overfitting if in fact you wanted to. Okay, but it's too good to be true. And here's the catch. The catch is this little detail about finding the optimum basis function, that's a killer. Okay? And in fact, that is the magic little issue that, oh yeah, often isn't really highlighted in a research paper. Let me put it this way. Well, let me tell you, okay, certainly it's true for some cases. So there's very simple basis functions like this famous case of decision stumps, where a decision stump is like a decision tree with a single node, right? It just says pick a single feature and have a single threshold, and then you just apply that one test, yes or no. Okay? If that's my basis set, then I have an efficient algorithm for actually choosing the optimal basis. Now that's a simple basis set, but it's still infinite because the choice of threshold value here is a continuum, right? So it's an infinite basis, but in fact it's really easy to take, you just check each coordinate, go through the training data, check every cut point in the training data, find a best cut. Right? The response is just a Boolean response vector, and I can take the inner product of that Boolean response vector with respect to the L prime cost vector. And so I can have a tractable algorithm, checks every feature, checks every cut, picks the best one. Okay? So certainly it's true, there are cases where we can devise efficient weak learning algorithms, coordinate picking algorithms. Okay? Unfortunately, in all the cases we're dreaming of, right, decision trees, neural nets, all that stuff, it's not an easy problem. In fact, it's an intractable problem. So here's a famous example, 2-layer neural nets. right? We have this first layer of these parameterized basis functions, and I said, don't pick L of them, let the learner decide. So sure, we'll let the learner decide how many basis functions to add. In fact, we'll just add an L1 regularizer on the output to guarantee, in fact, maybe the optimum solution has finite support, okay? And then we can say convex training for 2-layer neural nets. In fact, it's out there, it's already known, okay? Why is it not deployed? The reason it's not deployed is exactly this reason, which is even though the idea is out there and there's papers that discuss it, the unfortunate thing is that weak learning problem is one of the most famous intractable weak learning problems you can encounter, right? The problem of finding a hard threshold perceptron or even a soft threshold sigmoid network, 1 layer, that maximizes an inner product between its output and a cost vector, that's famously NP-hard. And not only is that NP-hard, it's NP-hard to approximate in any way you want to approximate. Additive approximation, multiplicative approximation, all bad, okay? So boosting would seem to offer this opportunity to train on these infinite bases. Unfortunately, pushes the difficulty of the problem into this coordinate picking problem, and that's hard, all right? So I know I'm just about out of time. Can I show you? I'm just going to show you one last crazy idea, okay, which is underexplored, but is intriguing and is kind of growing in popularity, which is, okay, the weak learning problem's hard, so I can't pick good basis directions, okay, but I have such a huge basis. I can fit anything, and in fact, the real problem isn't fitting the data. The real problem is going to be controlling overfitting, right? And in fact, do I really care exactly how I fit the data as long as I kind of fit the data with a smooth enough model? I would hope that the smoothness would give me some generalization. That kind of lame thinking, I guess, leads to this last thing I want to show you, which is forget about the weak learning. Run your coordinate descent, but why don't we just pick random basis functions? Why are we knocking ourselves out, right? Just pick a random decision tree, pick a random path for a tree, or pick a random first layer neural net model, okay? Is that really so bad? And shockingly, that almost works. And in fact, there are conditions under which you can show it works. So here's a bunch of technicalities, but if we actually look at dense linear models with an L infinity constraint. So we have dense linear models, but the density is not delta. The density is smooth. So it's a smooth combination over a set of bases, even though it's an infinite basis, okay? And it's not concentrated anywhere, so it's a smooth model. And let's just say that's the truth, okay? Or let's look at functions within that class of smooth. Here's what you can do. What you can do is that smooth class has some base measure, right? We can approximate it by just sampling from that base measure. So we can just draw a finite sample from that base measure. We get a finite choice of basis functions, and then we'll constrain ourselves to bounded, L infinity bounded linear combinations over that sampled basis. And quickly, you can show that you can approximate anything in the original class with high probability. So in fact, what you can show is just sampling random bases. Now, admittedly, we've constrained it somewhat here, but this is very intriguing, that you can just pick random bases and guarantee with high probability that for any target in that original class, you can, with high probability, there will be some approximator on this finite basis you sampled that is close in loss to the optimum, or to the loss that you had initially. And you can control it by sampling more basis functions. You can make that, with high probability, you can make that discrepancy arbitrarily small. Okay? Now, learning with random projections and random bases and so on, this is an intriguing topic that is actually being investigated quite heavily, at least in some pockets currently, and it is interesting. Okay? I think that the results that we actually have here and the algorithmic techniques that are out there in the world are very limited still, and this seems to me to be an area of investigation that it's really under-investigated. And it's worth checking into more. I would encourage you to do so. But you could see the risk here, because it sounds like a crazy idea, and you write your thesis proving it's a crazy idea in your context. Don't blame me, okay? But it seems like something worth knowing about. Okay, so that's all I plan to tell you about input space generalizations. When we come back after lunch, I'm going to change topics and now start expanding the models on the output side. Thanks.
I just have a couple of announcements. We are planning to have a group picture tomorrow, group photograph after the sessions tomorrow, 5:45. So we'll all gather here. If the weather is nice, we'll go out and do a picture in the union. Otherwise, we'll do it indoors. And the other thing I want you to mention is the MLSS mailing list is actually not for complaining about logistics, but it is for talking. If you want to send some information to everybody else, which is of broader interest to everybody else, please use that. If you have any complaints about logistics or you have any issues, either send an email to one of us, to me and Sergey, or to one of the volunteers that are responsible. So if you go to the homepage, you can look for the volunteers that are responsible. Thank you.